So from this data on compressibility factors, we can see that at cases where we have high temperatures and low pressures, the ideal gas law isn't going to cut it. We saw for some of those pretty significant deviations. So if you, for example, are a chemical engineer working with a gas under these conditions, which is quite likely, you won't get very good predictions from the ideal gas law about temperatures and pressures and things like that for gases maybe that you're trying to work with in a chemical reactor or something like that. And so you'd like an equation that gives you a better result than the ideal gas law. So one of the first of these equations that was developed, and one of the ones that has the most straightforward interpretation in terms of physically how it makes corrections, is what's known as the van der Waals equation. So this is the same van der Waals that describes van der Waals forces, and these are involved with this, of course. And so the van der Waals equation is a way to sort of correct the ideal gas law. You can think of it as fixing the ideal gas law for real gases. And van der Waals actually won a Nobel Prize for this work back in 1910. So this is the van der Waals equation. You add some extra terms to the pressure and volume on the left-hand side of the equation. So you get P plus A over V bar squared. So this is all in terms of molar volumes. You can write it out not in molar terms, but this is the way it's written out usually. Times the molar volume minus another constant B, so A and B, these are van der Waals constants, is equal to RT. All right, so this would be in the ideal gas, right? So this is our real version. In the ideal version, we wouldn't have those A and B constants, right? It'd be P times V bar is equal to RT. So what we've introduced are these terms here, this A over V bar squared and this minus B. And so the A and B are known as van der Waals constants. And these are empirical. So there's not like a theoretical equation you can use to calculate these. What you do is you measure pressure, volume, temperature data for gases under non-ideal conditions, and then you sort of fit it to this equation. So these are empirical. These are not necessarily something you can calculate on your own. And I don't expect you to. So what you do is you look this up in a table. So in fact, let me show you from your online textbook that I linked to from Moodle. This is a small table. You can get much larger tables. This just has 4 values on it though. So we have helium, nitrogen, carbon dioxide, and C2H4, ethylene. And so we can see they have different values of A, different units here, atmosphere liter squared moles minus 2, B in liters per mole. You can find this in different units. So this one uses atmospheres. You'll often see this in bar. But that is something to pay attention to when you do use the van der Waals equation of state, is to make sure your units all make sense. Okay, so going back to the van der Waals equation, what do A and B mean? What do they tell us about? So I'd like you to pause the video and think about that. Looking at the equation, mathematically, what do A and B represent about our molecules? Okay, so A leads to an effective decrease in the pressure. As A increases, that term is going to get smaller. We can figure this out by reorganizing this equation to write it as P equals RT over V bar minus B minus A over V bar squared. We can see the second term that has A is going to subtract, right? And so this is decrease in pressure, and this is going to be due to attractive forces happening in the gas. Because the molecules are pulling on each other, they won't hit the walls as hard, and so that leads to effective decrease. Now this scales as the density squared. 1 over V bar is the density, right? So if we remember V bar is equal to V over N, then 1 over V bar is equal to N over V, which is another way of writing a density, right? So it's a moles per liter. usually think in grams per liter, but this also is a way of measuring the density of the gas. So as the density increases, the attractive forces are going to get stronger, right, as the molecules are packed tighter and tighter together. Okay, so that's A. So if A is the attractive forces, let's look at B. So B leads to an effective decrease in V bar. And what this represents is the repulsive forces. And one way to think of this is that this accounts for the fact that the molecules actually do take up space, right? So molecules are not point masses. So this constant is effectively like how much space does the mole of these molecules take up, and then you have to subtract that from your molar volume to get what the true volume, the leftover empty space is. Okay, so these are based on experimental data, and we'll talk about this in class, but you can notice trends in A and B as you look at different molecules, whether attractive pulses or this repulsive forces of the molecules taking up space matters more for different types of gases. So you can get a rough idea of the level of attractive and repulsive forces in different gases based on their A and B constants from their empirical values. So in the next video, we'll look at using the van der Waals equation, how much, what's the comparison to the ideal gas law.